Let's take a look at the boundary conditions now that we know what the governing equations look like. And we will consider the boundary conditions for the mass and momentum equations first, and then we will put in the boundary conditions for the energy equation. So I'll go to a sketch of my domain. So I need to put boundary conditions at the edges of my domain, and this particular, the upper wall is split into two because we have an unheated part and the heated part. Okay, so let's, for the mass and momentum equations, where you have the flow coming in, we will typically put, if you can, we put a velocity boundary condition. So we'll assume that the axial velocity there is the average velocity that we want to get the required Reynolds number, and the radial velocity is 0. And where the flow is coming out, we will put a pressure boundary condition, and we will put it as 1 atmospheric. It turns out that the actual value is not important because a pressure gradient is what determines the temperature and velocity field. So if you change this value, you'll just change the pressure field by a constant. Okay, so typically where the flow goes out, you put the pressure boundary condition. Where the flow comes in, you put the velocity boundary condition. And then at the wall, we have the no-slip boundary condition. So Vz is equal to Vr is equal to 0. And similarly, that's for the unheated part, and this is for the heated part. So your velocity boundary conditions there. And then at the axis, we will, you can't have flow crossing the axis. So we have Vr is equal to 0. And also from symmetry, the radial gradients, so dVz by dr and dVr by dr and dP by dr all are 0. This comes from symmetry. Okay, so those are the boundary conditions for the mass and momentum. So if you had no heating, these were the boundary conditions you would put in. And this is similar to the laminar pipe flow module. But now we also are solving the energy equation, so we need to add in the boundary conditions for that. And where the flow is coming in, we will give it a temperature. The temperature coming in, we will set it to 300 Kelvin. And where the flow is, where the wall is unheated, we'll assume that the wall stays at that temperature. So we'll just say T is equal to T in. Here we have the constant heat flux. So using Fourier's law, minus K dt dr should be equal to that value of the heat flux that we put in. So it's essentially setting the radial gradient of the temperature. And nothing to do at the outlet, similar to the velocity boundary condition. It's just the pressure. And then also here, due to symmetry at the axis, we have dt dr is equal to 0. Okay, so those are the boundary conditions we will put in and when we get into the Fluent solver. Now that we know what our boundary value problem is, next we'll take a look at what is the strategy Fluent is using, and the Fluent solver within ANSYS is using to solve those that boundary value problem approximately.